So before I turn it over to Troy, just in case you guys probably are, but just in case, we're Skullspace. We are a non-profit here in the city. This is our space. If you're interested in becoming a member and seeing other talks like this and just being generally part of the community, and space and everything, come talk to me, or Ben, or Nate, really anybody who looks like they're a member, and we can meet up.
Okay, definitely, yeah. We'll connect at some point. I'll send that email to discuss.
Can people hear me back there, like at the hall? We're good? Don't need to turn up any mics or anything?
We're good. Louder and sadder.
Louder and sadder. This might turn it up louder. I don't actually know what I'm doing it. Looks like I'm on the right track.
Just lower your voice, Troy. It's the only way to do a presentation.
This is how I will talk. Okay, so I volunteered to do a little talk on general audio distortion, but more specifically how it applies to guitar distortion circuits. So this is kind of a classic pedal right here. It looks like a Boss manufactured brand. So these are just little circuits that you would plug your guitar into one end. It would change the sound, and then you plug it into your amplifier, you get different tones, and you can make neat things happen. There are all kinds out there. You can get things that put in delay circuits or equalizations. I'm focusing mostly on like classic fuzz and overdrive circuits. And we'll hear some sound samples of that as I go along. So just kind of a little bit of history myself. I got into electronics by playing with guitar pedals basically as an angsty teenager with nothing better to do and a soldering iron. So they're kind of near and dear to me. I wound up getting really interested in electronics, and I did an engineering degree in like electric circuits and computer engineering and stuff like that. Thank you. Okay, so on with the show. Some of the knowledge I'm going to try to impart on you guys is how these things work from a tonal perspective, like how they're changing the sound and why it sounds different, and also from like a circuits perspective, like how the circuit is making those changes. In some instances, I'm kind of sacrificing truth for clarity, because if I go into the real nitty-gritty details, it would be incredibly boring. So I'm trying to straddle a nice line of like interesting and practical and general knowledge transfer stuff. So I'm going to start out with some basic fundamentals about audio circuits here, because that's kind of key to how these circuits modify them. So audio signals, of course, if you play music, if you're not deaf, you generally know it's changing amplitudes over the course of time, and for us, it's like sound pressure waves. For electric circuits, it's very often a voltage signal. It can be like a current signal or a digital representation, but in analog circuits, you typically look at it as a voltage signal. So here's a little screen cap from Audacity, if you're familiar with that program. This is just me saying a test sentence. I think those are the actual words I say. And you can see like the amplitude changes as time goes on when I'm saying words. You can represent these signals in the time domain, which is useful for some analysis and some processing things, like a delay circuit is changing where this signal is happening in time, kind of. Or you could look at it in the frequency domain, which is this big confusing blob I've put in front of you. So before I go too much further, I'll kind of try to give you an intuitive understanding as to what this thing is. So if you have any time domain signal, some really smart French guy named Fourier found out you can compose this signal out of an infinite series of sinusoids mixed in at different levels. So these are like pure tones. Like I couldn't do one like a nice pure like ah or something like that, but it's a whole bunch of those added up. You notice this is the signal it's trying to make. It has these really sharp corners. You start out with something that's kind of the same tone, and you keep adding higher and higher frequencies, and that output signal is getting crisper and crisper and starting to approximate the square wave a lot better. So to get this spectrogram thing, and to kind of explain what it's showing you the frequency content on a piece-by-piece basis as time goes on for your recording. So for example, if we take a small piece like a fraction of a millisecond of this recording of my voice. You zoom it in, you can see it kind of looks like a sine wave that's really sucky and quiet at the beginning. You do this magical mathematical trick called the Fourier transform, and it turns it into this like spread of values. So here, the bright like red orangey color is saying there's a lot of amplitude for that frequency, and the blue is saying there's not a whole lot there. If we take a look at it in a little more detail, we can see there's a peak right here around 17 hertz. So if you were to just take out that little piece of signal, it would look something like that. Around 50 hertz, we have an even higher amplitude. And then around maybe 70 or 80 hertz, like the frequency gets even higher. And those kind of mishmash together to make our original signal for that duration of time. And you just do that for each time chunk, and it tells you what frequency components are present. So it's kind of neat. You can start to characterize things based on what frequencies are there. So for my voice, you can see there's this very clear like ladder pattern of like the tone I'm talking at, and these kind of like harmonic overtones that make my voice sound like my voice. It's kind of neat. So these spectrograms are useful for like if you wanted to see the difference between how a guitar sounds versus how a piano sounds. Like they're playing the same note, but the harmonic coloring is a lot different. And if you wanted to get a good look at that, this is where you would use that spectrogram. So a couple more intuitive examples. Here would be a spectrogram of a pure tone. Kind of try to ignore all this weird noise, this weird color pattern down here. I think that's a digital artifact. But it's just a straight line there, so for all time in this recording, it's just this one frequency. Here we have a rising tone, so it might be hard to see, but the waves are wiggling faster and faster and tighter together, and you can see its frequency is increasing on a log scale, so it looks a little flat, but it's showing you the changing frequency as time goes on. So for example, if we wanted to take a look at how a guitar distortion circuit is changing how your input signal sounds, you can look at it in the time domain. So this is me playing like a major scale. Maybe I'll play the sound clip here. So that's the plain guitar. And that's the same signal through a distortion circuit. So how do you glean that from this time domain signal? Like you can see everything looks kind of smattered out and it's just a big mess. But if you take a look at a spectrogram, you can see we have, like this is the original and the distorted signal. You can see our original content is reproduced here, but there's all this high frequency stuff that's like changing the actual tonality of the signal, and that's where you hear these differences. So that's kind of the base knowledge. I think you'll need to understand the rest of the material. So I'm going to go into kind of the main building blocks of these distortion circuits and then what makes those up. So here's another classic staple of like rock music is this big buff high circuit from Electro Harmonics. If you're interested in building pedals and stuff like that, you can generally find the schematics online, like make knockoffs yourself for relatively low effort. So in terms of circuit topologies, distortion pedals bear a lot of similarities to like a hi-fi or just a generic audio amplifier. And that's because a distortion circuit is kind of just a really sucky audio amplifier that adds a lot of things you don't want if you were listening to music. But if you want to color a guitar signal, maybe you do want some of these weird things happening to your signal there. So just about any distortion circuit is going to feature an input stage. Like your input signal would come in here, and that kind of just buffers it for the rest of the process. There's going to be your tone and amplification section, which will make it louder or maybe color it with an equalizer or impart other qualities to it. And then you have an output stage in most amplifiers as well. So like I said, the input stage is used to buffer weak signals. So if you have your guitar, which is kind of like a really sucky signal generator in terms of current capability, you can drive a really small load, like a 200 kilo ohm thing, like a really tiny electrical load. But as soon as you try to make it like do some heavy lifting into a 100 ohm load, it's gonna just piddle away into nothing. So you're not gonna really pick it up or hear it. And that's where a buffer circuit comes in. So a physical analogy of that, if you're trying to move a weight, you're pretty limited with what you can do with an amount of force and a lever. So your input signal in this case would be how much force you're putting in. And that's going to stay constant for this example. But if you add some leverage, suddenly you can move a much heavier load with the same amount of force. So that's kind of a qualitative explanation of what an input signal buffer is doing. So that is the operation of an input stage. The tone amplification stage is what generally handles your power amplification, like actually making the signal louder and adding like interesting content to the signal. So you got your plain Jane ukulele signal and you make it a little spicier, I guess, or whatever your tastes might be. The output stage in an amplifier is usually another buffer, and that's because like it can drive an 8 ohm speaker load, or maybe you want to drive a 16 ohm speaker load, but the point is, a user is going to plug something into this and it can have all these different characteristics. So a buffer is typically employed to separate that from what's making the modifications to the sound. Otherwise it might kind of like back ripple into the system and change how it's operating. For a lot of guitar pedals, however, these stages are often combined, and that's because you're plugging it into another amplifier. And an amplifier already has an input section, so you don't really need that output buffer in these instances. So that brings us to the basics of amplification. I'm pretty sure most of you know how to turn up a volume knob, and I'll go over that, but I'm also going to go into like how an amplifier can be bad or good in some respects for like audio listening versus guitar circuit. So an ideal amplifier is one that preserves your tonal qualities. So my voice is still going to sound like my voice, but it's just going to be a lot louder. So one way you can characterize amplifiers, one way, there's many, is by analyzing its transfer function, which is a mathematical way relating an input signal on my x-axis there, right, like so, to an output signal. So if we want to make a transfer function that makes the signal twice as loud, for every one value here, we go 2 values up, and we make this nice linear line. So to see in effect, like how a transfer function affects the input signal, what you can do is superimpose it on the y-axis or the x-axis here, and then you kind of see how it reflects onto the output axis. So in this instance, it makes a bigger signal. However, I don't know if there's such a thing as an ideal anything in this world. That almost never exists. So there's always going to be some faulty things to some degree. So for example, here we have a nice straight line, but just about any amplifier to some extent is going to deviate from a perfectly straight line. And that's going to change your signal a little bit. So for instance, this is a nice kind of like regular looking sine wave, but I kind of put it on like a high fat diet or something, or blown it out a bit. So that's going to sound a little different. To what degree, I haven't experimented with that particularly. A classic thing for PA systems, or sucky ones I should say, is crossover distortion. So that's when you have like two output transistors or two things that are driving the signal. So for one portion of the input, one transistor is giving like power, and for another portion of the input, a different transistor is giving the power. And there's got to be some switchover time between them. So that's when you get this like, you introduce this many-to-one mapping in your transfer function where for like these little values in the middle of my input signal, they just make like a flat kind of area of the output. So this is usually reflected quite a bit in like the chordal harmonic distortion rating you might see on a hi-fi amplifier. And this isn't really something you use in guitar audio circuits. It just kind of sounds bad in general and should be avoided. But this is the classic one here. This is called clipping, or like overdrive or saturation. It goes by many names. But this is basically when you have a transfer function that maxes out. Like Like it amplifies so far, but then it hits a maximum because like an amplifier is running between two voltage levels and it can't go past those. So that's when you get something like the input signal goes up and it kind of flattens out at the top or at the bottom. So that's kind of the core mechanic of many classic distortion circuits, two that I'll be analyzing. So this is the first pedal I ever built. That's not a picture of it. It looked like way shittier when I did it. But this is me breadboarding it a couple nights ago to give it some test signals and see what it did. So this is the circuit here. It's probably a bit much if you've never done electronics to any like hands-on degree, but we might be able to pick out some elements. Like these are variable resistors here. You have capacitors and resistors and transistors, which are like the bread and butter of these circuits. The way these circuits are usually drawn is quite handy because people tend to put the input side on the left and the output side on the right. So that makes it nice and easy to map the individual sections. So we got our input stage here, our tone amplification stage, and I called this an output stage, but these two are really kind of just the same one. That's a detail, you're not really too interested in that. So the operation of the input stage, which is kind of a current amplifier, if you're familiar with voltage and current levels and such. This is the basic topology for the output circuit. You have one voltage level here and another one there, usually your ground reference. And then this crazy transistory thing and a resistor that we see like right in there. So what this is doing is it's taking your input signal and it's kind of giving it more oomph with like a current supply. I'm trying to stray from the low-level details too much because they're really mathematical and kind of boring, so it's more a qualitative discussion here. So for instance, you have your voltage signal here, which remains relatively unchanged, save a voltage offset that you can't hear. But the current levels increase quite a bit. And that's when you can start driving bigger loads with your guitar signal. You give it more current to move. So here I put an input signal from my rusty, trusty, and really sloppy signal generator to the input, and I measured the output of the input stage. And you can see that it looks very nearly the same, save maybe some glitches and stuff, because it's like sitting on my desk and there's like fluorescent lights interfering and stuff. But at least in the time domain, you can see that it's not really changed a whole lot, which is what an input stage is supposed to do. Question?
How do you generate the signals? You said you generated an input signal?
Yeah, so what I used is, it's literally just a box that gives a sine wave signal out, and you can change the frequency, you can change the amplitude, and you can make it like a square, triangular sine wave. I actually have it in my backpack over there. I'm going to be playing with it later. Dedicated test equipment, I guess would be the answer.
We need to go for the space, by the way. If anyone has one sitting in their closet or wants to build it for a project, I'd love to go for the space.
Wouldn't we just use like a sound card?
I'd rather have it aside from, apart from computers, just standalone function generator.
You need a really good sound card to make a usable
Good one.
signal generator. You know, for maybe some projects like audio would probably be fine. Anyway, so that's the input stage. The tone and amplification stages are where it gets interesting. So you'll notice there's kind of a common topology between these two transistor circuits. Each one's acting as an amplifier. It's a general rule of thumb. Each transistor, at least in these circuits, is doing an amplification of something, be it current or voltage. So these guys are in charge of making the signal bigger, like in the voltage respect. And often you'll see in these stages there's a resistance at the top, a resistance at the bottom, and a transistor in the middle. We'll get into that a little more here. So the amplification factor, or the gain of the circuit, is dictated by these two resistors for most audio circuits, and it's approximately equal to this resistance divided by that resistance. So at this level, RA being twice as big as RB, you get an amplification factor of 2. If you wanted to make that bigger, you would just change one of the resistors to make this ratio 5, and you get something even bigger. If you want to get interesting and make things clip and sound a little different, you just make that difference like really big, and it starts to make things look a little more square and flattened out at the edges. So the same input signal to the output of our input stage, and then measured back at the output of the first transistor shows this kind of clipping in action. I'm not sure how well you can see these frequency plots. Can you see those in the back row, the purple and the black? Kind of. Can you at least see that they're wiggling a bunch? That's really all you need. So this one is like a nice pure sine wave, but only have like one frequency component. But you can see all these harmonics added in here. Like I'll try to trace it with my laser, and it's like really jagged and adding all these high frequencies. So the transfer function might look a little something like this. There's the output of the input stage, and then it kind of clips at these two maximum levels here. And then there's another amplification stage. I guess, by the way, this stage's gain factor would be about 100, so 10K divided by 100. Whereas this one is closer to about 2. It's, I guess, 1.2K plus 10K over 4.7K, it all balances out to about 2. But it's doing some more interesting things to the signal here. You can see these are like some nice, like flattened tops, and it's kind of like smushing them out a bit there. So you might surmise from these rounded corners that it means there's some kind of rounding going on in your transfer function. And that has the effect, I touched on that more later, but to make, where's my diagram? To make really sharp edges, it requires a lot of high frequency content. So much so that you would like drive dogs crazy and stuff, and it would sound like really bad through like a treble boosting circuit. So sometimes you want to kind of taper off some of those high frequencies, and that's what that stage is doing by rounding the corners. There we go. So that's kind of what this guy is doing. And I'll show you guys a sound clip of what this actually sounds like. I didn't record it before Signal because I didn't think to do that, but you can hear what it sounds afterwards. Something like that. You can hear there's a lot more treble quality to it. It's a lot crunchier sounding than a guitar, and that's basically what this circuit was designed to do. There we go. So that might leave you questioning. I've covered like what this thing does and what these resistors do to change the gain, but what's all this other crap in the circuit? Like what's this thing doing? For just an intuitive understanding, that's kind of setting your operating point of your transistor, like what its static output voltage would be, which kind of has the effect of shifting the transfer function to the left and right here. We can see we're kind of going, clipping in both directions here. It's hitting a maximum here and here, but if we shift where it's sitting, it's going to do the full spectrum here and then kind of clip out at the bottom there. Usually it sounds really sucky when you do it that way. Say that outright. It's a thing. So from a frequency perspective, you can see from this very relatively pure tone to here, we're getting a lot of harmonics. So it's a bit hard to make out, but the spaces between the peaks, I think, are about 5 kilohertz, which is the frequency of the fundamental. So like, for instance, like a musical harmony where people are singing together, they might do like different frequencies that are generally like multiples of each other. And that's why this still sounds kind of musical and not like just a bag of distorted crap. It has all these like ordered and evenly spaced harmonics. Further, this stage is kind of tapering them off. This is on a logarithmic scale. I could have made a better diagram, but I didn't. So you can see the output levels at the top end, like the high frequency spectrum, are kind of tapering down a little bit here, which kind of mellows out the sound a little bit. So that's what these like bias circuits do, is what they're known as, bias circuits. And then there's this other stuff in here. You see we have this capacitor labeled tone and like capacitors all over the place in here, which effectively act like frequency dependent resistors in a way. They present like one load at like one frequency, but a different load at another one. So that's how you can make circuits that amplify some frequencies and not others. So if you're familiar with guitars and guitar effects, the tone control usually changes how much high frequency content is in there. And that's exactly what this guy's doing. So if you see a bunch of like knobs and capacitors labeled tone, that's all that's doing. Sometimes you can even omit it if you just want to make a test thing to see if it's working and add that later. There's also this purple feedback circuit here. You can see it's taking some voltage from this transistor and feeding it back to the input stage here. If you recall from the diagram, I did have a line, although I haven't practiced this enough to remember where that diagram is. Yep, there we go. So we see this line coming from the output here and back to the input here, which is usually used to like limit the amount of gain in some very specific and fast ways. Back to where I was here. So for instance, it's actually changing the operating point, if you recall, by increasing the bias voltage there. So when this signal gets louder here, it's actually shifting where this guy's transfer function is sitting. So that's where you can get interesting kind of like changes to the character of your distortion. And a lot of times, like very similar circuits will have this stage done a little differently, and it can have like really different sounding results. And you can see here, just demonstrating the different frequency content. And just qualitatively, these sharp edges have become much more rounded, which is what you expect to see when you put on the high frequency stuff. So that concludes the Rocket. I guess I'll finish up with a case study of the Fuzz Face circuit here, which is kind of just like a really weird bag of garbage from an amplifier design perspective, but I guess that's what they were trying to do. So if you're familiar with Jimi Hendrix's work, he uses something very similar to this on tracks like Foxy Lady and a lot of his early stuff for that classic fuzz sound. So it's really dumbed down here. We have our input stage, which is one transistor and all of two resistors in this capacitor. And our output stage is again just another transistor with a basic drive control here and an output like volume, that's just a volume level right there. So again, I've breadboarded it up and gave it a signal and took a look at what it gave me as an output. So we can see here that these sharp edges seen at the output are even sharper than the ones that we got out of this guy. Like even this one's even rounded in the middle of this circuit. These ones are still quite jagged. So you can see here, this is the fundamental, or this is the frequency plot of our input signal. If I didn't mention this before, by the way, values over here are the low frequencies and values over here are the high ones. So this is the frequency of our input sine wave. And as soon as we distort it, we get all these peaks at like odd intervals of the input frequency that just sum up to make these really harsh corners again. So here's what that looks like in the time and frequency domains. And you can kind of glean different understandings of the circuit from each. So you can see here, this is me strumming a guitar chord, that the amplitude is allowed to go quite high when the amplifier is just, or when the guitar is just going straight into an amplifier. It kind of decays out. Whereas this guy is like, it kind of has more implied maximums and minimums there, which is a result of the clipping. You can also see the frequency plots here, the nice like comb looping of a strummed guitar chord. You can see all the individual notes and overtones in there. And then it adds like all this high frequency stuff in there with the distortion circuit. This one doesn't sound terribly good because I just made it with parts I had lying around. But if you tune one well, it apparently can sound something like what Jimi Hendrix's caliper and pedals were. lot harsher. That's for sure. And again, we're just driving the point home about the harmonic content here. So what makes this guy tick? We see a familiar output stage here. Like we still have the transistor and the two resistors here. I guess this is an explanation as to more how the output voltage is made. Let's go over this for a bit. And we still have this input stage here, but it doesn't have that same bias circuit going on here. So that's going to play into it later as to why it sounds a lot different. So maybe as a bit of an aside here, if you want to get an understanding, maybe drive it home a little more of what these components are doing in a circuit, you can kind of think of these resistors as like springs that are holding a giant rock in place. And you want to get the rock in like a nice medium level set by your biasing circuit so that it can like squish up and down without like hitting the bottom and making really hard jagged corners. Kind of a weird physical like drawing analogy, but it kind of works. So that's it, like kind of like the resistors kind of act like springs cushioning it from hitting the absolute extremes. But on the input stage, we only got the one spring, so it can bottom out quite easily. It doesn't have like a nice cushioning factor there. And in fact, because of its lack of bias circuit, it's got this feedback bias here. Kind of the rock, as it were, is hanging pretty low to the ground. And as soon as you try to drive it like any lower, you just get no signal anymore. So you're kind of, this input stage, which is supposed to be a nice like faithful representation, a nice current buffer, is actually distorting the signal like by an extreme amount. And that's what the transfer function approximately looks like there. So again, the bias isn't quite there. This is a measurement of the output of the pedal. If you give it a small enough signal, you can see the distortion from the input stage. It looks something like that. And here's what it looks like, the full-blown output, once again. And that's about all the material I had prepared. If you want to get into guitar, just like distortion and circuits and stuff like that, I can like one-on-one tell you a little more resources and stuff if you're interested. But
And you brought some stuff to play with too, right?
yeah, I did. Yeah, I left that set up over with my oscilloscope and all that too. I'd like to make some acknowledgments. I was a good boy this time and asked for permission for most of my images. So special thanks go out to RG Keen of geofx.com, Aaron Nelson of DIY Stompboxes, and some Boris signal processing. I found their image on Google. I don't know. I thought it was neat. And that's all I got. Any questions?
What software were you using for showing the frequency domain graphics?
Like the spectrogram? Or like
Yeah, spectrogram, not the screenshots of the scope itself, but the spectrogram.
That was just Audacity.
Audacity?
If you like click on the little down arrow, you can pick spectrogram.
Okay.
Does it quite nicely.
Would you like to speak to what a compressor does in terms of time frequency domain, or is that beyond scope for the moment? We can get into it later.
It'd be a really hand-wavy and sucky explanation.
Okay.
Well, thanks for having me, guys.